what up, what up? I'm the math teacher Goat, and today we are doing a full lesson in AP Precalculus of 1.12 transformation of functions. Now, 1.11 was probably the grossest lesson in all of Unit 1. 1.12 is my least favorite lesson in all of Unit 1. So buckle up, we're doing two things in a row that I don't like. So that's all right. We'll get over it. It's not all about me, except that it mostly is. Speaking of which, like and subscribe. Go to the description, download the notes. This is a full lesson, so you're going to want to follow along if you download and print or do whatever it is that you do with those things. Now, transformations is moving stuff, but let's get a warm-up on finding the slant asymptote. So again, this is just a warm-up, diving on previous knowledge. May not necessarily deal with what we're doing today. In fact, it really won't, but that's all right. It's just a good problem to do. We're going to take our factor x plus 3, and we're going to divide that into x squared minus 5x minus 8. All right, so it's a slant asymptote. We're looking for something in y equals mx plus b form. This will have a slant asymptote because the degree in the numerator is higher by 1 than the denominator, so all is well. X goes into x squared x times. Multiply that x to x plus 3, so you get x times x, which is x squared, plus 3x. Subtract the entire row, minus. U will go away. Minus 5x minus 3x is negative 8x. Drop down the negative 8. Then you ask yourself, x times what gets me negative 8x? Well, x times negative 8 gets me negative 8x. And we don't have to complete the problem because we're done. We're given something in slope-intercept form. Y equals x minus 8 is going to be our slant asymptote. All right? Now, the next problem says graph each. What do you notice? What I'm going to do is I'm not going to graph this using a calculator. Let's make a table out of this. All right, for at least the second part. The first part I really don't need to. It's a standard parabola. So if you plug in 0, you get 0. If you plug in 1, you get 1 squared, which is 1. You plug in 2, you get 4. So this happens. Whatever, it's asymmetrical, so whatever happens on the right side, the same exact thing will happen on the left. Okay, at this stage, if we don't know how to do a standard x squared parabola, what are we doing here? Okay, so that will happen. Now with g of x, why don't we pick a couple x values, and I might need to pick more. Plug it in, see what happens. So let's pick negative 2, negative 3. Why did I do negative 3? Negative 2, negative 1 is what I meant to say. Negative 2, negative 1, regular 0, 1, 2, and we'll leave some space for any more that we have to do. If you plug in negative 2, you get negative 2 minus 2, which is negative 4. Negative 4 squared is going to be 16. Negative 16 plus 1 is going to be negative 15. That won't help us at all. If I plug in negative 1, I'll get negative 1 minus 2, which is negative 3. You square that, you get 9. Throw a negative in front of it. Negative 9 plus 1 is negative 8, so that won't help us at all either. Good start, math teacher Goat. Idiot. Just joking. I'm not an idiot. I'm smart. Plug in 0, you get negative 2 squared, which is 4. After you negative 2 squared is 4. Negative 4 plus 3 is negative 3. You plug in 1, so that's 1 minus 2, so that's negative 1. Negative 1 squared is 1. Negative 1 plus 1 is 0. You plug in 2. 2 minus 2 is 0, so 0 plus 1 is 1. Let's add a 3 and a 4 to this. Let's add a 3 and a 4 to this. Didn't mean to put that 4 there. Doing a bad job. All right, so if I do 3 minus 1, I get 1 squared. So the same thing that happens here is going to happen here. So you'll become a 0. And if I do 4, that's the same thing as plugging in, so you'll get negative 3. All right, so we have a direction here. Okay, I can't graph u and I can't graph u, but I can graph 0, negative 3. I can graph 1, 0. I can graph 2, 1. I can graph 3, 0, and I can graph 4, negative 3. Okay? So I have another parabola again, but it's flipped upside down, it's moved over, it's moved up a little bit. I wonder if any of these things, the fact that this shifts over, like the vertex, that's what that's called, is right 2 and up 1. I wonder if that negative 2 and that positive 1 have anything to do with it. This is upside down. I wonder if that negative out in front has anything to do with it. I guess we shall find out, and we'll find out here using this thing that I stole from the internet. So, rules for transformations of functions. If I give you a function of any kind, whether it's a quadratic like I just had, or it could be a linear, any function, if you add a number, you move it up. If you subtract a number, you move down. Now, in pre-calculus land, anytime you move up or down by just simply adding or subtracting a number on the outside of everything, we call that a vertical translation. So moving up 4 is a vertical translation of 4. Moving down 4 would be a vertical translation of negative 4. Okay, so just the verbiage of AP pre-calculus is slightly different. If you're working within a parentheses next to x, that's when you move either left or right. Now, this is bizarre. Okay, this is where it gets different. A positive number, so a plus c, means you actually move left. It's opposite of what you're used to. So if you kind of go back up here, notice that this is minus 2. Now you would think that, oh, minus 2, you move to the left. No, you don't. Minus 2, you go to the opposite, and we actually ended up moving our vertex right 2. So within the parentheses, within x, if you're adding, you move left, and if you're subtracting, you move right. Now, we use phrases like horizontal translation of negative 6. So this guy up here would have been a horizontal translation of positive 2. That's how you would say it in AP Precalculus. Okay, if you throw a negative in front of the entire function, what you do is you just reflect it over the x-axis, which essentially flips it upside down. If you throw a negative in front of all of your x values, what you do is you reflect it in the y-axis, which means you kind of flip it sideways. Okay? Now, if you multiply a number to the whole thing, right? If that number is positive, it's going to stretch it vertically, which means if it looked like that, it's now going to look like that. Okay, so the same width is going to happen, but it just gets 2 times bigger, and so it appears steeper, which is why if you graph a parabola like this, right, and you multiply 2 to it, it'll get skinnier. Now, you won't see how it looks like it's, what in reality is doing is getting taller, but it's not going to get taller technically because it's infinite. So you multiply a 2 to it, it vertically stretches. If you multiply a number in between 0 and 1, like a half or a quarter, it gets smaller, it vertically shrinks. Okay, now the vertical stretch or the vertical shrink is called the vertical dilation. So what you would say is if you were given f of x and I gave you 2 f of x, you would say a vertical dilation of 2. All right. Similarly, if we multiply, instead of multiplying the whole function by a number, if we multiply just the x values by a number, what you're going to do is it's going to do the opposite, just like it did moving left or right. If you multiply your x value by a 2, it shrinks it. Okay, it actually makes it skinnier horizontally. So if it looked like this, okay, it's now going to look like this. So the height stays the same, so let me make it a little bit longer. The height stays the same, it looks steeper, which it is, but it actually gets skinnier. That's if you multiply a 2 to it. If you multiply a half to it or a quarter to it, actually what's happening is it's becoming wider. Okay, now we call that a horizontal dilation. So if I multiply a 2 times every x, what you're doing is you're dilating it by a scale factor of 1 over 2. Okay? Or if you were to multiply this by a 1 over 2, you're horizontally dilating it by a scale factor of 1 over 1/2, which is 2. So we're going to have to explain that stuff. We're probably going to refer back to this chart from time to time. Again, you can see why this is not my favorite. It's just kind of a pain in the butt. Now what I'm going to do is I want to leave these words up here as we get our feet wet. So let's do that. I think we're okay if we do that. All right. So 3 things are happening here. Okay. Describe how to transform f of x. What you're going to do is you're going to work within the innermost x first. You're going to do your movements first, then stretch, shrink, flip, whatever. 3 things are going to happen here. Okay. We're going to move left 1, up 4, okay, we're going to stretch vertically 3. Okay, so vertical stretch, or we'll do vertical dilation of 3, and then this gets reflected over the x-axis. So let's say that. Left 1 is a horizontal dilation. That says dilation. Moving left 1, -1. By moving up 4, it's a vertical dilation of +4. By multiplying the whole thing by 3, we have ourselves a vertical dilation of 3. And by multiplying the whole thing by a negative, you're going to flip it upside down, which is reflect over the x-axis. This one's a little less involved. This one, all you're going to do is move it down 7. Since you're multiplying the x by a quarter, it's going to be 1/4 horizontal dilation, and 1/4 just means you flip that up and make it 4/1, which is 4. So we're going to go down 7, which is a vertical translation of -7. And since you're multiplying that by x, it's going to be a horizontal dilation of 4. Gross, 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 gross. Let's draw pictures. Be careful, by the way. If you see something like f of 2x minus 4, you have to factor, and that actually becomes f of 2x minus 2. So you move things and then you dilate. So in that case, what that means is move, and we'll just write it right 2, and then a horizontal dilation of a half. If that happens. It may not. It's rare. All right, now let's take a look at each graph. I am terrible, 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 terrible at these. Terrible at these. So I'm going to do the best that I can, make the prettiest pictures that I can, and we'll see what happens. F of x plus 4 is a vertical dilation of 4. All we're doing is moving it up 4. So let's notice some key points here and try to move each of those points up 4. 1, 2, 3, 4, put a dot. 1, 2, 3, 4, put a dot. 1, 2, 3, 4, put a dot. 1, 2, 3, 4, put a dot, and try to recreate that drawing using the dots that we have. Okay. The minus 4 is happening within, so that's going to be minus 4, which is right 4. So that is a horizontal translation of positive 4. So we're going to take every point and move it to the right. So let's use, here's a point here, here's a point here, here's a point here, here's a point here, here's a point here. Let's move all 5 of those to the right 4. 1, 2, 3, 4, put a dot. 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 1, 2, 3, 4, covering you, put a dot. And we'll just use a completely different color to draw out that weird shape that we just had. Okay? Lots going on. So what we're going to have to do is we're going to first move right 2, then up 5, and then reflect it over the x-axis. So we're going to take, I think it's 4 points again, or 5. 1, 2, 3, 4, 5. We're going to move each point right 2, up 5, reflected over the x. Okay, so here we go. Right 1, 2, up 1, 2, 3, 4, 5. So here I am. Reflecting this guy over the x has me going down 1, 2, 3, 4, 5. So you put a dot there. Let's do it again. Right 1, 2, up 1, 2, 3, 4, 5. Hold on, I think I screwed that up. 1, 2, 3, 4, 5 is going to go up to 6, which means reflecting that over the x-axis has me going down 6. Here's a point here. Right 1, 2, up 1, 2, 3, 4, 5. Here we are up 5. So reflecting it over the x-axis has me going down 5 underneath. Here we have this point. Right 1, 2, 3, 4. I'm sorry, right 1, 2, up 1, 2, 3, 4, 5. So we're 3 above the x-axis, so reflecting that over is going to be 3 below the x-axis. Let's go right 1, 2, up 1, 2, 3, 4, 5. So we're 5 above, reflecting it gets me 5 below. Ooh, 5 below, like a convenience store. My kids love that place. I feel like one of these is wrong. I feel like one of these is wrong because I went too far for that one. No! No, I went too far for that one. Yeah, that's much better. All right, let's draw that out. This is why I hate this section. I'm bad at drawing pictures. I'm really bad at drawing pictures. I'm bad at drawing pictures. All right, so now what's going to happen is we're multiplying a number in front of f of x. And with this guy, since the number is a half, we have ourselves a vertical dilation of a half, which means the height is going to get half the size from where it is to the x-axis. It's going to become half the size of where it is to the x-axis. So this height is up 3. Well, now you're up 1.5. That one's touching the x-axis. Let it keep touching the x-axis. That bump there is up 2. Well, half of 2 is going to have it be up 1. You're touching the axis, still touching the axis. And now what we have is a shape that is literally the same exact width left to right, but is half as tall. Okay? Gross. All right, so what we're going to do with this guy is this guy basically is saying, look, you're going to move it up 2, and it's going to get 3 times taller. So when we deal with the 3 times taller part, let's deal with that first. Let's make it 3 times taller, and then we'll move things up. So I'm going to identify 1, 2, 3, 4, 5 dots there. Okay, let's make this, it's on the x-axis, so let's make it 3 times taller. Well, you can't. So now let's just move it up 1, 2, and there's a dot. Now this thing is at -2. So to make it 3 times taller, you're going to multiply -2 times 3. That's going to go down 1, 2, 3, so down to -6. Okay, now we move it up 2, bang, bang, and there you have it. This is at 0. Make it 3 times taller by multiplying it by 3. You can't. Now add 2, up 1, 2. You're already at 1, so let's make it 3 times taller by multiplying 1 by 3. 1, 2, 3. And now move it up 1, 2. You're at 0, so make it 3 times taller by multiplying it by 0. Nothing. Go up 1, 2, and those are our new dots. Okay, then you just draw yourself a nice straight line. Draw your nice straight line. Try to make that like a curved oval looking thing. And there you have it. Okay. Now the way we're going to handle this one is we have a bunch of stuff happening inside the parentheses. First off, you have a horizontal stretch, which means you're going to make it half as wide. Then you're going to move it left 3. So let's do that first. And we're going to use several steps for this. So we're going to make it half as wide, move it left 3. So let's do that part first, and then we'll deal with the minus out here and the plus 1. All right, so you're over here at -3. Making it half as wide is going to move you to -1. Now, moving that part left 3 is going to have you go left 1, 2, 3, and you put your dot right there. Okay, here's another dot. Half as wide is going to put me at -1/2. Now go left 1, 2, 3, and leave it right there. Here's a new dot. Half of 1 is going to be at 1/2. Now move that left 1, 2, 3. Get it right there. Here's a dot. That's at 2. Half of 2 is 1. Now let's move that left 1, 2, 3. Move you over just a little bit more, much better. And here's our final dot. Half of that is going to be at 1.5. Move that left 1, 2, 3. Now I have those 3 dots, and basically what we're seeing is a skinny version of that little triangle hoopy thing to the left. Now what I need to do is I need to flip that over the x-axis and move it up 1. So I'm going to take each dot, flip it over the x-axis, and move it up 1. All right, so here I am with this dot. Flipping something on 0 over the x-axis does nothing to it, but moving it up 1 will put me right here in the middle. Okay, here we are, 2 down, so flipping it over the x-axis has me up 2, and then move up 1 more. Flipping this dot over the x-axis does nothing, but moving it up 1, puts me here. Flipping this dot, that one, over the x-axis moves it down, and then moves it up 1. This is terrible. And then that last one, flipping it over the x-axis does nothing, but moving it up 1 puts me there. So at the end of the day, this god-awful problem, again, you can see why I hate these. Just with a fiery passion of 1,000 suns. That's what you get. Not pleasant at all. All right, let's do some math. This guy is pretty easy. It's saying, look, f of x equals blah, 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 blah. So let's find g of x, which is blah, 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 plus 4. So literally all you're taking is that guy. So g of x, right, is just going to be f of x, which is x squared minus 3x plus 2. And then we're going to add 4 to it, like that. So it just ends up being g of x equals x squared minus 3x plus 6. That's no big deal. However, this next guy, slightly bigger deal, has shades of AP calculus in it. You'll see when you get there. Now we have to find f of x plus 4. That means replacing every x in f of x with x plus 4. So that's going to be f of x equals x plus 4 squared minus 3 instead of x, x plus 4 plus 2. Now this guy foils out. It's a perfect square trinomial. So that becomes x squared plus 8x plus 16 you are going to distribute out. So that's negative 3x, negative 12, and then you are going to be plus 2. So let's combine like terms. Let's combine like terms. So let me see. H squared is just h squared. 8x minus 3x is 5x. And then you have 16 plus 2 plus 2 is going to be, is 20. And so that's what g of x is going to be. I don't know why I put f of x up there. It's g of x equals. That's all right. I got the right idea down anyway. All right. Now what we're going to do is we're going to take 2 times f of x plus 4. So remember, f of x is that guy. So 2 times that whole thing, x squared minus 3x plus 2, and then we're going to add 4 to it. So g of x is going to equal that. So that's 2x squared minus 6x plus 4 plus 4. And really all we have to do is just combine those two 4s. And last time I checked, a tooth 4 is for chewing. Tooth 4? Tooth 4? Tooth 4? What's a tooth for? Tooth. Ooh, another one. Now I want 1/3 of f of x plus 2. So that means I am going to take 1/3 of this whole thing. But first off, what I need to do is I need to replace every x with x plus 2. So you become 6, x plus 2 plus 3. So the first thing that we're going to do is do distributive property in here. So 1/3 drops down. You become 6x plus 16, or 12 rather, plus 3. 1/3 of 6x plus 15. And so at the end of the day, g of x is going to be 1/3 of 6x, which is 2x, and 1/3 of 15, which is 5. All right. All right. These are a lot friendlier. Given the table values for f, g of x equals f of x plus 2, find g of 2. All right, well that means g of 2 is going to be f of 2 plus 2. Well, what's f of 2? Oh, if x is 2, then f of x or f of 2 is 10. So f of 2 is 10, so this becomes 10 plus 2, which is 12. G of x is f of x minus 2 plus 1, so let's find g of 4. So g of 4 is going to be f of 4 minus 2 plus 1. F of 4 minus 2 is f of 2. F of 2 is 0. So 0 plus 1 is 1. I like the table ones a lot better. They're a lot friendlier. A lot friendlier than what we were just doing. G of x is 5 times f of x minus 1. Find g of negative 1. So that is going to be g of negative 1 is the same as 5 times f of negative 1 minus 1. F of negative 1 is 12, so that's 5 times 12 minus 1, which is 60 minus 1, which is 59. My age. I'm kidding. I'm just kidding. I'm 23. Given the table of values for f, there they are. Ugh. G of f of 3 of x minus 1, close it, plus 2. So that's going to be g of 2 is going to be f of 3 of 2 minus 1, close it, plus 2. So that's going to be f of 3 times 1 plus 2, which is f of 3 plus 2. F of 3 is 8. 8 plus 2 is 10. Fun. Fun. So much fun. So much fun. Last page, baby. Give me the graphs for f. Has a domain. Oh, give me the graph for f has a domain of negative 4, 3, and the range of 3, 9. Let g of x equals f of negative. Holy crap! Find the domain and range. All right. So what we have here is we have horizontal shift. Okay, moves left 5, moves up 2, flips around the x-axis. Basically, if you're dealing with a horizontal shift, the horizontal shift is the only thing here that's going to affect the domain. Because by flipping it upside down and by moving it up 2, that only affects the range. So what happens is the domain is moved to the left 5 times. So the original domain is negative 4, 3. So let's move that to the left 5 times by subtracting 5, and that gives me a new domain of negative 9, negative 2. Okay, so that part is not too bad. The range is going to be the thing that is affected. So what's going to happen here, what we could do first is let's deal with the reflection. So there's our range. If I deal with the reflection first, reflect first, what that does is it takes both of these values and makes them, it's reflected over the x-axis, makes them negative. So what that does is 3, 9, and this is going to be weird, you ready? Because these are y values, right? 3, 9 reflected over that is going to be negative 9. Well, here, let's do this. Let's just play dumb. Okay, let's play dumb. Okay? When you reflect it, it's going to be negative 3 and negative 9, which becomes negative 3, 9. Oh, hold on. Sorry. Which becomes negative 3, 9. Negative 9. And then common sense takes over and says, well, wait a minute, that's out of order. Negative 9, negative 3. That's what we have so far. But now what we're going to do is, since you move this up twice, our range is going to have me adding 2 to both of these, giving us a final range of negative 7, negative 1. So there's my range, and there's my domain. Tricky, 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 tough stuff. Tricky, 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 very tough. The function f of x equals x squared minus 1 is transformed into the function g of x equals x squared over 5 minus 1. So basically the only thing that happened, right, is you divide that by 5. Now I can write g of x as 1/5 x squared, which means this is a vertical dilation. And when you do vertical dilations, you use the actual number as its scale factor. So this is a vertical dilation by a factor of 1/5. Okay? Nothing crazy, nothing wacky, nothing crazy, nothing wacky. Now, is this the same type of problem that we saw above? It is. Ugh. All right. Well, let's just do it. One more time, since there's nothing directly in front of x here, there's no like horizontal dilation. So the only thing that's going to affect the domain is this horizontal transformation where we move to the right 1. So our domain, which was originally negative 1, 3, right? Our domain, we're just going to add 1 to that, plus 1, and that gives us a domain now of 0, 4. Which all of these are 0, 4, so, you know, thanks for nothing. But now what we have is we have a vertical dilation, and then we're going to move it up 3. So basically this is the same exact problem that we saw up here, just a little bit more complicated. My range is 2, 4. I'm going to reflect first by multiplying it by negative 2. That gives me negative 4, negative 8, but common sense tells us that's backwards, negative 8, negative 4. Now by moving it up 3, we're going to add 3, we're going to add 3, and that gives us a final range of -5, -1, and that is going to be A. Okay, so I guess those problems aren't so bad. They're just, I don't like them. I really don't. A function f of x is not explicitly given. That means when they give it to you, they're not going to curse. Explicit. In the xy plane, the graph of the function g of x is the result of a sequence of transformations applied to the graph of f of x. Vertical dilation by a scale factor of 3. So something like this is going to happen. Horizontal dilation by a factor of -1. So this is going to happen. Translation of 2 units up. So you're going to do f of x plus 2. And translation of 6 units left, which means x plus 6 on the outside. Now this is where you have to be really careful. So we could set up 3 g of x, because they want it to be called g of x, is going to equal 3 times f of. Now listen, if we're going to do 2 things, this is the way we must do it. Okay, you must do negative parentheses x plus 6, because the plus 6 has to be with a regular old x. Then outside of it, in a parentheses, you could throw that negative there. And at the end of it all, you can add 2. So this part is kind of crazy, kind of tricky, but that is a function that would define those transformations. And let us transform into the end of this lesson. It's awful. I'm not a fan. I really hate translations, transformations, dilations, whatever you want to call it. I'm not a fan of it, but you know, you got to do it in AP Precalculus anyway. So what are you going to do? Sue College Board? Like and subscribe, please. Make sure you go to my YouTube and type out AP Precalculus 1.12, and that will give you these videos for you to watch and further understand your learning so that you become good, smart AP Precalculus kids. Thank you for watching. We're a couple more sections before this unit is over, so we're moving along. Okay, well, make sure you've been watching all of them. If you haven't watched any of them, what are you doing? Thanks for watching. Love you guys. Bye.